Hello, everyone. My name is Luis Ortiz, and today I will be talking to you about um, electronic circuit designs. I'll be going over the basic understanding of what an electric circuit looks like and the basic components of an electric circuit. Um, so yeah, let's get started. Okay, what is an electric circuit? So an electric circuit is it's a controlled path in which it allows for an electric current to flow through and for an electric current to be transferred from one place to the other. Here we see an example of a 3D example of what a basic electronic circuit looks like. It first goes, you see that it first goes through the negative charge, and here there seems to be a switch, and this switch depending on whether if it's on or off, will determine if this light bulb gets turned on. And so yeah, here we see that the light bulb is turned on because the switch is on. It's connecting both the two sides. No, it's connecting the whole current to itself. Um, and yeah, so the switch is on right here. And over here we see 2D model of what an open circuit looks like, which is what this circuit is. It is a battery, which is a source, and the electric current paths. So here it goes up, and then keeps going through the circuit, and here's an on or off switch right here. And here it's off because it's not connecting it to the other side of the current, you could say. And yeah, once this is connected over here, this light bulb will turn on, which is a load, and it will go through all around, which is what makes it an electric circuit. So the objects shown here are the battery, the wires, which are conductors, and the light bulb. And so this is a mistake. This would be a light bulb. Um, But yeah, usually the wires, which is the conductors, they're made up of copper because copper is a good metal to transfer electric currents. And it's also a really good metal to transfer this because it's really durable and it's cheap. Not cheap in quality, but cheap in price, um, meaning it's more affordable. So say you want to do a project and you need to build an electric circuit, for example, copper is really good because it's flexible, it's durable, and it's affordable, and it'll save you lots of money. So here, there's two examples of me with basic electric circuits that I did with IEEE ops. Here we see me connecting to the breadboard. So this is video one. So in that video, we see that there is a switch and the battery connects here, and then the electric current is transferred to the switch. And depending if the switch is on or off, it will determine if the LED light gets lit on. And then there's another wire that connects back to the other side of the voltage. But yeah, and here's another example. This example is using a resistor. But we'll get into that in a bit. So yeah, here, depending whether if I press the button, it determines if the LED lights up or not. So if I do press the button, it lights up. If I don't, then it doesn't light up. Um, and yeah, I think that's the basic gist of it. Okay. Okay, so when talking about electric circuits, it's very important to understand Ohm's law to begin this slide. So Ohm's law is the voltage which is equal to the current times the resistance. Um, so the voltage would be considered the battery or um, any type of battery that will have electric current to um, be created from because you need a source of a battery. And the currents would be like the wires, and the resistance would be like resistors. So some basic knowledge to know is that as you increase the voltage, your current increases, meaning more push is more flow. And if you increase the resistors, your current decreases, which means more resistance and less flow. Um, if you do an example with the breadboard and you have a really high resistor, your LED light will be more dim than it would be if you have a resistor with the really low resistance. Um, and and if you have really low resistance, then your LED will shine more because there's less resistance, meaning more electricity gets passed on to the LED light. And it's really important to have resistors because if you were to just transfer electricity to the light bulb or to the LED, it'll more than likely burn out really quickly and easily. So resistors are really important to understand and to know, and to have in your currents. And Kirchhoff's law, there's two key concepts. Here we see that the junction theorem. So the sum of a current into a specific junction in the circuit equals the sum amount of current out of the same junction. It's basically implying that what goes in goes out, and the amount of electricity or the high voltages of currents that you put in to an electric circuit would be the same that you get out. It's really simple. It's what goes in goes out. There's nothing much to it. And the loop equation implies that around each loop in a electric circuit, the sum of the M's electromotive force or voltages of energy source, such as batteries and generators, is equal to the sum of potential drops or voltages across each of the resistance in the same loop. It basically implies that the voltages around the whole current are going to remain the same if it starts like that. So you won't get like a high voltage on one side of the current and then a low on the other side because it's all connected into one. So that's basically all there is to that. The types of currents. So in direct currents, there's DC, um, which is in just another name to call it DC or direct currents. So this is basically it flows in a single direction, and its main use is to supply power to electric devices and charge batteries. So examples to think of with DC or direct currents would be like when you connect your phone to charge, there's a direct current going to your phone, charging your phone. Or when you turn on the television, it's connected to the outlet on the wall. And it's just one current that goes up to your television to start. And also electric vehicles when you charge them, because you want your vehicle to be charged, so you charge the batteries. And alternating currents, also known as AC, it changes directions periodically, meaning it doesn't really have one stable direction to go. It's not always a direct current, which makes it an alternating current. And it's common to have these in powerhouses or household buildings and offices because it lights up the whole building and office. So types of circuits, I mean. There's a parallel circuit, which means that there's two more paths in the current, and the voltage is the same. So here we see the battery, and then there's more than one path to go to. So here it goes up, and then it goes down, and it does all sorts of loops. And in a series circuit, there's one path flow, so it just goes up. There's a resistor, goes over here, resistor, goes over here, resistor, again goes back to the battery. So you can see that there's a clear difference in parallel circuit and series circuit, and it's kind of similar to direct current. So here we see that a direct current is kind of similar to series circuit in terms of like um, the topic of understanding circuits, because these are the currents that are coming here. This is a direct current, and then here a parallel circuit. There's alternating uh, paths here, so you can kind of connect two and two together. So talking about my topic, in which I think is important for the future, or something that's going to be developed in the future when it comes to circuits, is electric vehicles. Here we see a little bit more complex electric circuit. So here we have about the battery pack, which is a source of electric energy, and the mode is the loader. The motor is the load, and the electric current basically goes um, to the battery management system, which goes to the controller, and then it it starts up the motor. And EVs usually use lithium batteries um, today, um, but as we keep advancing, there's been more talk about creating solid state batteries, and you're going to see why in a second. So why is solid state batteries better for EVs? So to start off, here's an image a of a solid state battery on your right and a lithium battery to your left. And you see that it's less impactful than the solid state battery, and there's more liquid here. And here we see your anode and your cathode, which um, start up the battery in a sense, you could say. So the reason why solid state batteries are better, um, it's it's much more safer because here we see it's compact and there's not a lot of liquid flowing around, and this liquid is very flammable. So if the car starts on fire, this will more likely be more flammable than solid state batteries, which is more compact and there's not really much going on the outside. So it's a lot safer to have solid state batteries. It also weighs less and it's more compactful, meaning it takes up less storage, and less storage means that less storage and less weight means that the car will be lighter, which is also another good thing. So the car won't be as heavy, and there's more energy, so there's greater MPG, and yeah, it reduces the cost overall. So in today's world, um, Toyota announced that they want to start making solid state batteries. Um, sorry, they want to start making solid state batteries. Common battery for a Toyota car in 2026. They want to start manufacturing this, and it'll be up by 2030, I believe. They mentioned this, or at least they want to start this project because solid state batteries are better for EV cars. And so Tesla average range is from one charge is 400 miles, and the Toyota 2027 solid state battery project would allow for one charge to have 600 miles, and it would charge between 20 minutes. So one, it's more convenient because you charge your car faster, and besides all the other benefits that we mentioned, and solid state batteries are also cheaper, meaning that the new Toyotas can be a lot more um, affordable, well, depending on popularity, as you see. And here we have Toyota 2027, wait, 2026, 2027 project with the solid state batteries. This is just a example of what an EV Toyota car looks like. And here we have a Tesla, which is also another EV car. And yeah, so these are my sources, and thank you so much for your time.